So yesterday we stopped what did I say? Number 18, 2:18. Chapter 2, number 18. So yesterday we stopped, we discussed the problem of a point moving in space and going from, say, point A and B, say at time t1 and time t2, and you know, say, you throw a point particle, and it goes from point A to point B, following a certain trajectory, right? And the question is, if you look at the motion of this system as a whole, why this trajectory? Why the solution of the equations of motion, in this case, they produce this particular trajectory out of an infinite number of possibilities that the particle could follow, right? This is a rephrasing of the problem of the motion in classical mechanics. Instead of asking ourselves what is the motion of a body, of a point particles or whatever for a given initial position and initial velocity, I can ask myself why out of all the possible trajectories in going from a certain point to another point, the actual trajectory is that one. Right? Why that one? And if I can answer this question, I have another way of solving the equations, right? Because I discover out of this infinity of possible trajectories, the actual trajectory followed by the body, and then I've solved my problem as well, right? Like if I solve the differential equations. And I said this is actually a very nice and intuitive manner of thinking of the motion in space. And probably this was the original idea that people had by looking at how objects behaved around them. But then, as I said, unfortunately, the mathematics involved in deciding which one is the actual trajectory is more complicated than the mathematics of the differential equations. So they were stuck for many years. I mean, probably this idea of the motion was already present in ancient Greece, so before Christ. But then they had to wait the 1800s, essentially, when the calculus of variations was developed, and this problem could be tackled mathematically, right? But we are lucky we live after these people, so we have this mathematics and we can discuss this problem directly. Notice that if I want to, for a second, think of this, I don't know if you have discussed this in quantum mechanics, but this is exactly what happened in quantum mechanics. Have you discussed this or not? Well, just that if you look at an electron, in quantum mechanics, actually, indeed, the electron goes all these possible ways. That's the reason why it behaves in such a weird manner. In quantum mechanics, actually, the electron goes all the possible way, and each of these paths is weighted by a function that he mentioned, the exponential of some quantity. And when you sum over all these trajectories, you get the amplitude for the electron on going from here to there. Okay? So in a way, this is also nice, a nice picture of what is going on, because it brings together classical mechanics and quantum mechanics. Okay? Classically, the electrons simply follow a single trajectory from A to B, and that's it. And we will study this problem. But in your mind, you should bear the idea that actually in the real world, all trajectories are followed by the electron with different weights, and then you know, when when you compute the amplitude from going from here to there, and then you square and you get the probability, that's what you are doing. So this is an alternative picture of course, you can always solve Schrödinger equation and find the same results, the amplitude from going from A to B for the electron, but the two pictures are equivalent, and it's useful to bear both of them in mind, okay? But here in this class, we don't discuss quantum mechanics, but just classical mechanics. So for us, it's true I can consider all these possible trajectories, but still have to decide which one is the actual one, the one that actually the body takes in going from point A to point B. And the way you compute this trajectory is through another principle that is called Hamilton principle that you find in your textbook. And it simply states that if you consider the motion of your system, okay, be it a point particle or a more complicated system, just from a time, let's call it t1 to a times t2, okay, is such that this quantity, that is a line integral, so you take the line integral from time t1 and times t2, okay, so you compute the integral along a certain path. This is called a line integral, okay, you have done this, right, you know what I'm saying. So you compute this line integral from going from t1 to t2 on each of these paths, and of this quantity, just the Lagrangian. So you know that the Lagrangian depends on your generalized coordinates and the generalized velocity, and maybe explicitly the time. So you integrate along this path from time 1 to time t2, okay, and this quantity that you compute, okay, the principles say it has a stationary value, meaning that is either either a saddle point or a minimum, right, because it's an extremum, okay? So the Hamilton principles say that this quantity for the actual motion, so actual motion has a stationary point. So in general, this is a function of the path you take, clearly. And this function, if you take the derivative, we will see what kind of derivative you are supposed to take, will have a 0 that corresponds to the stationary point, okay? In general, this stationary point is a minimum, but it could also be a saddle point. We should look at the second derivative to decide, but it's not important. So another way to say this is that if I take the variation of this quantity, right? So I say this quantity has a stationary point for the actual motion. That means that at the actual motion, if I take a variation of this quantity, so I take a variation of this line integral of the Lagrangian, this vanishes, right? This is equivalent to what I wrote there. At the stationary point, think of a minimum, right? If you take a minimum, then a minimum by definition is a point in which if you move a little bit about, this change is 0, right? Because the derivative is going to be 0. You just take at the first order, okay? It's like a Taylor expansion about the minimum. It has, by definition, it has 0 first derivative. So at the first order, there is no variation. Okay? So that's very nice, I think. It's a completely, you see, completely different. I'm not using Newton's equations here. I just give you this principle. You look at the problem. The actual motion is the one that gives you a stationary point for this quantity. So let's see what kind of differential equations do we get by using this Hamilton principle. Hopefully, I get back Lagrange the same set of equations that we derived before that we call Lagrange equations, right? So if I use this principle, then I have to do this mathematical step. We'll do it in a second. This implies calculus of variation, so it implies some intermediate steps, but the outshot of this should be Lagrange equations back. And so then we can go home happy because we have rederived what we are going to use many times in the future. Okay. So as I said, you see, this is not such a trivial. You see, here it's not the usual variation. You are used to have a function that depends on some variables, and you know what to do if you vary these variables, how this function varies, and then you take a derivative of an integral, right? This is the next level of abstraction. Here you are not varying the independent variables, you are varying the function itself. I don't know if this is clear. You see, because I'm not varying the t. The t it just is whatever it is, it flows. But I'm varying the function of t. So it's sort of the next level of abstraction. Instead of varying the variables and seeing how the function changes, here you vary the functions, and then you look how some other quantity, for instance, this integral, is going to change. And you want to sort of take the derivative or the variation of this quantity as you vary your functions. Okay, that's why it's called calculus of variations. And you understand that it's the next level of abstraction, so it took some time to get used to for the mathematicians and to develop the same tools that the same tools you have for finding extremal points for functions, you have to find here. Okay, so let's see how it works. And the way it works, maybe let me do it in one dimension first, and then you see here you have as many dimensions as degrees of freedom. This I runs through the number of degrees of freedom because these are the generalized coordinates. So this in general is an n-dimensional problem. And of course our brain is not very well equipped to deal with more than, well, if you are optimistic, 2 dimensions, but really it's 1. And that's why we use mathematics, right? We are not very good at, already in 3 dimensions, we are not very good at visualizing things. And in 1 dimension we are good, and 2 dimensions so-so. But that's not a problem because we call our friend the mathematicians, and they tell you how to deal with problems in many dimensions. But let's start from just 1 dimension that is nice and we understand better. So on this side, I want to just study this problem, or maybe just a basic problem. So I have so 1 dimension that I call just x. So 1 dimension, okay? And you see the problem there is to find, say, now I just have 1 function, right? Instead of q, I just have 1 function that I call y, and it's function of just 1 variable, x. In this case would be t, right? Okay, and I want to find the function y of x such that that quantity there, such that I, in this case, what is y? Is the integral from x1 and x2, or if you prefer, call x t. I just switched to x because it's the usual notation for 1-dimensional problems, right? Such that a function of y and the first derivative of y, in this case would be dot, and maybe x explicitly integrated over x, right? In such a way that this quantity has a stationary point. So this is just the same problem, simplify down to one dimension. So what do we mean by stationary point? That so now I'm in one dimension, so I can draw on the blackboard this function. So I have this function, and I go from a point x1 to a point x2, y2, y, and say by stationary point means that if I vary by a small amount my path, that variation vanishes, right? So I look for a stationary point with respect to variation by neighboring trajectories, okay? So now the problem is how do I parameterize this small change in trajectory, this variation in the function? You see, I need to, in some way, parameterize how I go from one of those, so from this one, say, down to the other one, right? If I can do that, I would have a parameter, and presumably, if I take a derivative with respect to that parameter and I impose that to be equal to 0, I'll be able to discover my stationary point, right? So you see, the trick here is to sort of rephrase the problem in such a way that I can use the tools I already know from what I knew about calculus. So you see, what I want really is I have my function y of x, and then I change it by a little amount so that I parameterize. This becomes a function of x and then some parameter. And you see, the definition that I want is something like this. I start from my original function y of x that identify the one with alpha equal to 0. So this is, say, if you wish, this is the actual path. And I deform the actual path by some new function, right? This new function is the difference between, say, this was the original one and this. So at each point, this is eta of x, right? For each of these points, the deformation. And the amount of this deformation, you see, it's a deformation that depends on the point at which you take it. So it's not a translation. It's really a deformation. So I go from this curve to this curve, and I parameterize this change by this parameter alpha. I see, well, I don't see what is this clear, or? It's just a parameter, but you see, is the parameter that parameterize the amount of change. So this, say, is this trajectory here. This is y x of 0. I want to vary this parameter, this curve, so I move from this curve to another curve like this, for instance, and at each point, the amount of this change is given by this new function, eta of x. And the amount of this is parameterized by the factor alpha. So you see, this was x of 0, and this is y x of alpha. That is the sum of these two. So in this way, I have formally translate the problem that I had, that I start from a curve and I deform this curve a little bit in mathematical terms. I have the deformation is this one away from the original curve, and the amount is given by this. And this is a small function, so that this is a small deformation from the original one, because this is all I need. Is this any clearer, or? So now you see I can replace everywhere my y of x by this y x of alpha. Therefore, my integral now must depend explicitly on alpha. That's exactly what I want, because this way I can take derivative with respect to this quantity and look for stationary points. So this I, that is this integral, is a function of alpha x1, x2, simply because I have replaced my y's with y of x and alpha, y prime, this is a derivative, x of alpha, and x that is just x. So as I vary my trajectories, what is the definition of a stationary point? Now I succeed in translating this problem in varying a parameter alpha. Therefore, I can just rely on the usual idea that the stationary point, the condition for a stationary point is just what? This is this now is just a usual function. It's a function of some variable alpha. Therefore, if I take the derivative of this function with respect to alpha, and I compute it at alpha equal to 0, if this is equal to 0, this is exactly the condition for having, right? It's like the derivative for having that original trajectory be the actual one, right? Because alpha equal to 0 corresponds to taking the actual path. So I compute the derivative of this quantity with respect to alpha in alpha equal to 0, and I impose that to be equal to 0. That's the definition of a stationary point, and therefore is the condition for a stationary point for this y of x to be the actual path, according to Hamilton's principle. So now I've fixed everything. I only need to do this, to take this derivative in here. So let's do that. So I want to take the derivative of this quantity. So you see it's not completely trivial because it's the integral. This function is the integral of functions. So I'm taking a derivative of an integral. Okay? So I want to take the derivative of this. So d alpha is what? Now, here you have the usual problem that mathematicians spend a lot of time arguing about. You need a lot of conditions. If I have a derivative of this quantity, what I want is to go across the integral and take the derivative of what I'm integrating. And I want to be sure that this is correct. And in general, it's not correct, as you know. I mean, you cannot switch around integration and derivatives. They do not commute if you use quantum mechanical language. But if these are reasonably well-behaved functions, meaning they are continuous, they are not spiked, so this is okay. You can find that in the math books. So let's do that. We just act with the derivative inside the integral, right? So I pull the integral outside, and I now act with the total derivative on this function. Again, here I have the usual thing. I'm acting with the total derivative on with respect to alpha on a function that is a function of y, which itself is a function of this alpha. So the way to do that is to take partial derivative. That is, I take the partial derivative of this function f with respect to each of these arguments, and then the argument derivative with respect to alpha. Okay, what we did last week for the other problem. So this depends on y. So the first term is just the partial derivative of f with respect to y times the partial derivative of y with respect to alpha. So that takes care of the first term. Then you have another term. So you have dy prime alpha, right? And then this, but x does not depend on alpha, so I don't have to worry about that, okay? So that's all I have, and have the integral over dx. So how about this? Well, let's look at the let's look at this term here. This is okay. I'll keep it the way it is. What is this? What is this term? How can I rewrite this term? This term is the integral from x1 and x2, right, in dx of what? Yeah, I mean, it's like df. You see, this is, so this is like the second derivative, right? Because this itself is a derivative. So this term is just df dy, right? df dy, d2 y dx d alpha, right? Yes, sorry. Right. Like this, right? And this I can do by parts. You know about this thing that you can do integrals by parts. Huh? So if you do this by parts, this means this thing is df dy prime dy d alpha. So I take this by parts. So I take the first term minus the integral. So this has to be computed from x1 to x2. And this I have the integral of the dx of this part here, df dy prime, times what is left there, that is dy d alpha in dx. Right? I do this integral by parts by identifying the d. Here you have the second derivative with respect to dx and d alpha, so I take the partial derivative to respect dx, and I do it by parts. So I have the first term is this, right? Minus, I have to take then the derivative with respect to x of the other term, times whatever is left there. You know about doing these integrals by parts, right? Now, how much is this term here? Well, the thing is that, you see, when I define this variation between 2 points, or maybe here, you see it's a variation of the function between these 2 points, but the condition is that at the end points, I do not vary anything. You see, I do vary my path, but I keep the end points fixed. That means that this quantity at the end point is just the same. It does not vary, so this gives no contribution. So that's a problem in which the boundaries give no contribution, okay? So I'm left, so from this second term, I'm left with only this term here. So I can rewrite this as this integral. So the first term is whatever it is still there. But you see, I have a common term that is the partial derivative of y with respect to alpha, so I can factorize that out. And I have, so this minus this term, so minus dx df dy prime everything that multiplies dy d alpha, that is here and here, and that's it. But what is dy partial derivative with respect to alpha? You can see it here. It's just alpha. It's just eta, sorry. So you see, I have here just eta. So that's a situation in which I have an integral, right, between two points of some function of x times another function dx, right? And I want this to be equal to 0. But this function is arbitrary, right? It's completely arbitrary because it's the arbitrary function that defines my arbitrary variation away from the actual path. And if this is arbitrary, this integral to be 0 means that this quantity here must vanish. Therefore, from here, I see that the stuff that is in between square bracket must vanish. Okay? And therefore, this condition, the vanishing of the derivative of my integral with respect to alpha in alpha equal to 0 is equivalent to the vanishing of whatever I have there between square brackets. Okay, so this is nice because you see I'm falling back on what I know. This was a calculus of variation problem with integrals, but the vanishing, the stationary point for this integral now implies that your function f must satisfy this equation. And I hope you recognize this to be Lagrange equations in one dimension. If I replace x with t and y with q, just one generalized coordinate, that's exactly Lagrange equation. So you see, Lagrange equations can be understood in this language as, the solution of the Lagrange equations is that trajectory that gives you a stationary point of this quantity that we define to be the integral. So we have sort of proved that the Hamilton principle is equivalent to Lagrange equations. Okay, but actually this is this equation you can use it in general, right? If you have a problem of variations, right, you want to find some stationary point, some extrema in some problem, you can use those. In fact, the people use them to solve geometrical problems, for instance. Okay, but for us, those are the Lagrange equations related to the motion, the classical motion of your body. Okay. Yeah, I'm sorry. Yeah, you're right. It's like this. Sorry. In fact, we can, now that we have the equation, we can, well, first let's see how it works, and then we generalize to the n dimensions, because still here we are, for instance, you see, you can discuss geometrical problems. So let's stay in one dimension on the plane of the blackboard. And for instance, what is the shortest distance between 2 points on the plane? Right. This is a problem that I have 2 points on a plane. In this case, the blackboard. What is the path, the shortest distance between these 2 points? Of course, everybody knows that it's a straight line, but it's nice. Can I prove it mathematically? And you see, it's a problem in this form here, because the distance here is the integral of ds. If I call ds the small, a small distance, infinitesimal distance on the plane, ds, right, this ds, that is also, of course, equal to what? I introduce Cartesian coordinates, so this is dx squared plus dy squared, right, by I guess, Pythagoras, how it's called, theorem or whatever, right? Small ds. And you see the total distance between point 1 and 2, I can call it I, as I did there, and is what? Is the integral from 1 to 2 of ds. So this is the quantity, this is the distance. I still don't know whether this distance is a straight line or something like this. This is general, because I just go from 1 to 2 along some trajectory, but I haven't told you the trajectory. But the shortest one is going to be a stationary point for this quantity. So it's a problem very similar to this one. And in fact, I know that if I take the Lagrange equations of the function that I have here, the solution of those will give me the shortest distance between those 2 points. Okay? So this is a nice example of a problem, geometrical problem, that I can tackle with the same technique that I'm going to use for classical mechanical problems. So what is the function there? Well, I just replace ds. I need some Cartesian coordinates, so I replace ds with my so I integrate from point x1 to x2, right? I take out dx from the square root, so I have dy dx square dx, right? I just rewrote ds in terms of Cartesian coordinates, and I pulled out dx, right? I have dx dy square. And so you see now this is my, what I call here f. And you see, actually, it depends on the velocity in a way, because it depends on the derivative of y with respect to x. Of course, it's not the velocity here, because it's just the derivative of this of the function y with respect to x. But so if I impose now, let's solve now Lagrange equations for this function f. So I have to, so what is df dy in this case? No, the partial derivative of f with respect to y. You see, this is y dot in a way. So there is, right. What is df now with respect to y dot, or prime, let's call it? That is the derivative of that. That, again, is y, right? It's y prime divided by square root of 1 plus y prime square. Okay? Y prime for us now, it's dy with respect to x. So I computed this term and this term. This actually vanishes, so I only have my Lagrange equations are rather simple. I just take the derivative with respect to x of df dy that we said is just y prime 1 plus y prime square, and this must vanish. So my solution is the solution of this differential equation. What is the solution of that differential equation? You see, if the total derivative with respect to x of this quantity must vanish, that means this quantity is a constant. So that means y prime square root of 1 plus y prime square must be some constant that I don't know, we call it constant. And this I can solve, right? You multiply both sides, and that gives you that y prime must be this constant divided by 1 minus this constant square. You check. Anyway, this is another constant, right? So let's call it A. A is the constant divided by a constant. And so this, again, you know how to integrate this term, because that tells you that the function, that this solution of this problem must be this constant times x plus maybe another constant that usually is called b, because you are taking a derivative. So this is the solution of your problem, and what is that's the equation of what? Right, so you have rediscovered that you can fix A and B by telling what are these 2 points, right? So that you determine the straight line going through those 2 points. But you see, this way you have rediscovered what you knew in a way. Well, I don't know. In fact, why do we know that this is the correct answer? Okay. Without doing the computation, it's not clear, but by experience, I guess, you know that the straight line is the shortest. So you see, indeed, well, at least in this case, we have shown that by solving this equation, I solved the original problem that was more complicated, that is, which among many possible trajectory was the one giving you a stationary point for this quantity that we define. And so this is a nice example. There are many examples. You find some in your textbooks, so if you want, you can try and solve them, and geometrical examples, I mean. And you can use this technique. It's a branch of mathematics, so it's not our main concern here. So I only want to, so far we were in one dimension, so you see that the generalization to n dimension is sort of trivial, because all you have to do, so instead of having that integral that I wrote and then I erased that was there, you have to look at variation of a quantity, right, that we set from 1 to 2 of a function that now is a function, as I said, of n in general, as many generalized coordinates as degrees of freedom that you have, and so you have this. But you see, this is just sort of, I mean, it's just a superposition of many one-dimensional problems, so you can easily guess that the solution is just the generalization of that equation there, where you take, I'm sorry, here was the Lagrangian, where you take the Lagrangian, and each time, so x is t, and now instead of having just one y, you have q1, q2, q3, qn. So you just put q dot I down here, right, minus dl dqi equal to 0. So instead of having just one equation, you have n equations, and by now we know that this set of n equations are called Lagrange equations. So I don't have to prove any new things, and I go to directly to the dimensions. Or n degrees of freedom. Okay? questions? So essentially now we could we could start with some of the applications of this. But before, there is one last thing that I want to discuss. Well, actually two. One we discuss on Friday, one now if I have time. And I want to discuss a little bit what I said about conservation laws from this point of view. You know about conservation laws from your previous studies in classical mechanics. And you know that they are very useful because they tell you that some quantities are conserved, right? I mean, through the whole motion, okay? And if these quantities are conserved, that means that, you know, if you write them in terms of your generalized coordinates, those quantities are a constant. And then what is specific of these quantities is that usually they only imply the velocities, not the acceleration, right? For instance, if the energy is conserved, you know that the energy is the kinetic energy, for instance, maybe plus potential. You don't have accelerations there. You only have velocities. So what is nice about that? If you only have velocities, that means you only have differential equations of the first order, right? Because the velocity is just one derivative. While the accelerations are a little more complicated because they are second derivatives. And so in general, if you can map your problems into a sufficient number of conservation laws, right, then you can solve you can solve the problem by solving just first order differential equations, and that's in general simpler. Okay, so you get the trajectory by looking at the conservation laws. So that in fact is going to be one of our strategy in solving in solving many problems. So, but let's look. Now we have our Lagrange equations, and I want to look for conservation laws. So in this language, what is a conservation law? Usually, so they are function of, as I said, they are function of your coordinates and your velocities, but not the accelerations, okay? And these are function of these quantities that remains constant, as I said, during the motion, okay? In this language, such constants are called first integrals of motion. And you understand why, because as I said, in a way, you have integrate once because you don't have any longer the accelerations that you had in the original equations of motion, right? So that's why they are called first integrals. And really, they are very useful, right? Because they sort of help you out in solving the problem. And let's look at first. So how do you derive in this language the first integrals? Well, that too is very nice, I think, because there is I don't know if you have you may have already discussed this somewhere else, but these first integrals, they are related to symmetries of your system. Have you already met this concept that conservation laws really come from symmetries of your system? I give you an example. And for instance, what happens if you have homogeneity in time? That means your system does not change explicitly with time. We are used to that. Usually, this is the assumption that we make, right? So how do you translate in the language of the Lagrangian the fact that the system is the same at different instant of time? Usually that's what you assume, right? That this classroom, tomorrow you come back and it's going to be the same. It's not going to be bigger or smaller. I mean, you hope. Usually that's our experience of many solid structures, okay? So how would you translate that in terms of the Lagrangian? Assume that you have a Lagrangian describing this room. So if there is no explicit change in the room from today to tomorrow, that means you don't have an explicit dependence on time in your Lagrangian, right? So that means that the partial derivative of your Lagrangian with respect to time gives 0, right? Remember that the Lagrangian in general is a function of your generalized coordinate, generalized velocity, and maybe the time explicitly. But now I'm assuming that this system, the Lagrangian that describes this room, does not explicitly depend on time, and that guarantees you that when you come back here tomorrow, the room will be more or less the same. And this mathematically means that there is no explicit dependence on time in the Lagrangian, so that if I take the partial derivative with respect to t, that vanishes. So what does this result? What do I get out of this? Well, let's look now at the total derivative of my Lagrangian with respect to t. This is a different animal than this. We already said that and discussed it, right? This is the total derivative with respect to time, not the partial derivative. So that one, in general, does not vanish. And in fact, what is this? Yes. So is the partial derivative of L with respect, well, first you have t here and you have t here. So with respect to qi, right, times q dot I. Now let me introduce a notation that is going to help us and simplify our lives. That you see, every time, usually I should write this, right, okay, but there is a convention that was introduced first by Einstein, that if you have repeated indices that are the same, you assume that you are summing over those indices, okay? So we agree from now on, unless we really want to stress the sum, that if I write this, I mean that I'm summing over this index. That will save blackboard and paper for you. So I have the dependence on the general coordinate, but I also have the dependence on the velocity, so I have to put dl q dot I, q what? Dot I, right? And then I also should put that, but I'm assuming that that term vanishes, okay? I'm assuming this, so this is all. I only have these two terms. So what can I do with this? Well, let's look at this term here. And let's use Lagrange equations. Lagrange equations for this qi tells me that this quantity, that is this quantity here, is equal to this quantity here, right? So I could replace, so I have the q dot I, and then I replace partial derivative of the Lagrangian with respect to qi with this d dt dl dqi dot. Right? I'm just using Lagrange equations, right? So this total derivative of the Lagrangian becomes this term plus, I haven't done anything on the second term, so that I will write simply like this. But what is this? You see, it's like it's the total derivative with respect to time of this times this. Look. right? Because first this hits this first term, it gives me q dot dot dl qi, that is this term. Then you have q dot I times the derivative with respect to time of this, that is exactly this. So the sum of these two terms can be rewritten as the total derivative of this single term. So you see, the entire thing is just the total derivative of what? I take this on the other side, right? So I have the total derivative of q dot I dl dq dot I minus L, and this vanishes. Just by assuming this. And as I said, this means that your system is time invariant. You have homogeneity in time. As before, if this total derivative of this quantity vanishes, means that this quantity is a constant in time, right? And in fact, this is a famous constant that I call the energy. Take the simplest system, that is the one for which the Lagrangian is just the kinetic energy, or say, of a particle, right? So then this term here, that is qi dot d. Now I put the so I take a system that the Lagrangian is just the kinetic energy, that is a function of q and q dot, minus some potential. Okay? So here I have this, so I have dt dq dot I. There is no q dot in the potential, right? Minus the Lagrangian, that is t plus u. Okay? Now the kinetic energy is just, it's like if you take the partial derivative of the kinetic energy with respect to the velocity, and you multiply by the velocity, what do you get? Is 1/2 m q dot square. So you take a derivative, you get a 2, but then you multiply by q dot, so you get back the kinetic energy. So this is just twice the kinetic energy, right? So this thing is t plus u. So this quantity indeed is what you are used to call the energy, because you see it's the sum of the kinetic energy plus the potential energy. That is not the Lagrangian, that is the difference between the kinetic energy and the potential energy. So indeed, this constant is a very special one, and is the energy. And what we derive here is that if your Lagrangian does not depend explicitly on time, meaning that the system is invariant for time changes, then the energy is conserved, because if I take the time derivative of the energy, I get 0. That means that is a constant in time. That means the energy is conserved. So this is a beautiful result, because you see you have linked a geometrical property of space, time, if you wish. You say time, I mean, nothing changes in your system as time clicks, okay? Then the energy is conserved. For instance, is the energy of that clock conserved? After what we said, can you answer right away, is the energy of that clock conserved or not? Well, but I don't hear any clicking. Is the clock all the same? Is it homogeneous? I mean, that system, is that homogeneous? I mean, is it invariant for changes in time? No, because by definition, a clock, to be useful, must change with time, right? Otherwise, okay, if it's broken, that is time invariant, but then it's not a very good watch. So a clock, by definition, is something that changes in time. Anything that changes in time is a good clock, right? If you look at the sun moving during the day, that's a good clock, because the position of the sun changes as time goes by. So by definition, a clock cannot conserve the energy. It must in some way lose energy, and the losing of energy is your clock. So there is a simple example of this derivation of theorem that links symmetries in your systems with conserved quantities. Okay? Any question?
This formula is true for any system.
For any, well, remember that we are using the Lagrangian, so we are using Lagrange equations. So remember the two assumptions that we made, that you could write the generalized coordinates, so that you didn't have any work done by the constraints, and we are writing the potential, so the system is conservative. That, I mean, meaning that you can write the potential energy for the forces. So if these two assumptions are satisfied, then this is true. And this, in fact, is the way you understand conservation of energy in classical mechanics. You do have conservation of the energy simply because the Lagrangian does not depend explicitly on time. That translated in plain English means that the system is invariant, does not change with time. Okay? And now we can apply the same idea. What if the system is, so here we look at the invariance of the system with time. How about homogeneity of space? Right? Here we were talking about time. Now I want to apply the same idea to space. What if your system is the same as you translate the system, as you move around in space? So you're not moving in time now, but in space. And by this argument, I should get some conserved quantities, and we want to what this quantity is going to be.
Can we explain last formula in terms of image?
In terms of what?
Of image.
Of this one?
Yes.
No.
Not this result. First.
The one in time or the one in space?
When we found y of x equal to ax plus ax plus b.
Yeah. No, but that was a different thing. There I was using Lagrange equations to minimize, to find the solution of a problem with the shortest distance. This is a different thing. Here I'm assuming this. I'm using the same equations, but now I'm doing a no,
It's not possible to explain this.
the conservation of the energy using a minimum, a stationary point of something. Is that what you are asking, or not?
Is it possible to when we have two particles, to go from one particle to the other, we can move in line trajectory.
In space.
Yes, but how about the other trajectory? Is it why because the energy is lost, or
I'm not sure. So you're asking me if you go from this point to this, on this trajectory, the energy is conserved. Is the energy conserved if I go there? Is that what you're asking? If you go a different trajectory? In general, no. In general, no. But I mean, there are two. I'm not sure I see the connections. I mean, this was a problem of finding these equations out of the Hamilton's principle. Now this is, forget about that. Now I'm using Lagrange equations and some assumption about the symmetry of my system to derive conserved quantities. So the conservation of the energy is based on the fact that I satisfy Lagrange equations, and clearly those are satisfied only for the actual trajectory. In fact, the actual trajectory is defined to be the one that satisfies Lagrange equations. So if you move on a trajectory that is not the actual one, in general, the energy is not going to be conserved. So I said, what happened if now, so this was the energy, so let's, but I hope I'm not sure that I mean, this is a very powerful point of view that we are embracing now. I mean, you don't look at the energy as a quantity that then you check out whether it's conserved in that specific system. You see, from now on, the only thing you need is to check the Lagrangian whether there is a little t around, right? And if it's not there, you already know that the system conserved the energy. You see, that's right? I mean, that's something, I think. And similarly, let's do the same exercise. Before it was a displacement in time. Now I want to do a small translation. So I go from R to some R to the same R plus some rigid translation that I call epsilon, some small vector. So if this was R, I move by a small vector to a new point here, okay? And I want to understand how the Lagrangian changes as before, right? I wrote how the Lagrangian was changing under a small displacement in time. Now, how does it change by a small displacement in space? Let's use Cartesian coordinates because it's simpler in this case. And I look how my Lagrangian changes if I do this. And as usual, this change is just dl, the dependence of R, right? So R, maybe I have many of these if the system is made of more than one point, but the displacement is a single one. So I take the system as a whole, I translate it. Okay? So I have this, right? This is the change of my Lagrangian. And as I said, the dr, this delta is just epsilon, right? By definition. So this change can be written simply as this, where this is a constant, okay? It's the same for all. You see that this is only possible, I mean, I want my Lagrangian to stay the same under this transformation, and you see that this is possible. This is a constant and arbitrary vector, so this is only possible if this quantity vanishes, right? I mean, this variation can be equal to 0, or because this is arbitrary, that means necessarily that each of these must vanish. Now, again, I use Lagrange equation, that one, actually equations because I have a of those, I have a copies of these coordinates, but I write dl, what is r a vector dot, that's just the velocity, right? So I call it va, minus nothing, because here I have dl, dr vector a, but because of what I'm assuming, that the Lagrangian does not change under a translation, this must vanish as well. So you see, I have discovered another conserved quantity, because again, I have the time derivative of this quantity that must vanish. So this quantity must be a constant, as before the energy. And in fact, what is this quantity? Right, it's P. So that means that the momentum is conserved. You see, it's rather, actually, it's rather subtle here. Well, first, it's very interesting. The invariance for under translation, rigid translation in space, implies the conservation of the momentum in the corresponding directions. So a very profound statement, as before with the energy. So the energy is related, the conservation of energy is related to movement in time, to the system remaining the same as you change the time. And the conservation of momentum has to do with translations. As you move in a certain direction, if nothing changes, if nothing is changing as you move through a rigid translation in that direction, the momentum, the corresponding momentum is conserved. So again, you have linked two things that in principle look disconnected, that is conservation of some quantity with properties of space-time. You have linked the two. You see, actually, if I rephrase this in terms of generalized coordinates, I get an even more powerful statement, because essentially what I get that every time the Lagrangian does not depend, so every time the Lagrangian does not depend, well, let's call it QA, so a specific generalized coordinate, okay? That means that the generalized momentum that I define to be exactly dl dq dot a, so this I can call PA, right? That means that P dot A is equal to 0, right? That is this statement. So every time in your Lagrangian you see that you don't have an explicit dependence on some of the generalized coordinates, then this implies that the generalized momentum that is conjugate to that coordinate is conserved. That we will use over and over, because it's a very useful concept, and usually this is called a cyclic coordinate. That is, a coordinate that does not appear explicitly in your Lagrangian is called cyclic, and in fact implies that the conjugated momentum, the P defined by this, so this I guess is a definition, is conserved. As I said, this has to do with the invariance of your system under translations. So if you wish, this has to do with the homogeneity of space, three-dimensional space. Okay? Is that the question? Yes.
This happens only if the Lagrangian is not time.
No, this. So if the Lagrangian does not depend explicitly on time, you have the conservation of the energy. If the Lagrangian does not depend explicitly on one of your generalized coordinates, the momentum defined to be the partial derivative of your Lagrangian with respect to that, to the velocity of that coordinate, is conserved. And you can guess that the next step is that how do I get the conservation of the angular momentum? And that has to be with some invariance of the system under rotation, according to this general idea. Okay? So I leave it as an exercise to derive the same for, so assume that your system is invariant under rotations. technically it's a space that has this property is called isotropic because it's the same in all directions, right? You have spherical symmetry. Think of our universe. On a large scale, our universe is homogeneous and isotropic. On a small scale, it's not, because clearly here is different than outside this door. But if you scale very much outside our galaxy, you take all the galaxies, you take a big average. On the average, this is a fair assumption that the universe is more or less the same, right, on a very large scale, and isotropic. And you may wonder, are these two independent concepts or not? Can you have a space that is not homogeneous but isotropic, or vice versa, a space that is not isotropic but homogeneous? Well, that I leave it to you to think about it. But let's just assume that it's homogeneous and isotropic. And you see in such a space that happen to be our universe on a very large scale, then by this argument you have conservation of the momentum in all three directions, and also conservation of the angular momentum. So that's the ideal situation. You have a lot of conserved quantities because you have your momenta are all conserved and your angular momenta as well. And of course also the energy, because that should be conserved, even though for the universe that's not so obvious because it's expanding, right? So maybe it's not. So this was to show you that indeed this Lagrangian approach is rather powerful because it allows you to derive these things. And I hope now in your mind you have this connection between symmetries of your system and conserved quantity. In fact, this mathematically, so let me just restate this, then we stop. As I said, assume that the Lagrangian does not depend on a given coordinate. So let's say your Lagrangian does not depend on a given coordinate that I call Q sub j. Then what does that imply? That your Lagrangian equations, that are these, right? I in general, for the I equal to j, that is the cyclic, I said, coordinate, so for this special value, this term is equal to 0, therefore this is equal to 0, and therefore this quantity in between the brackets that you can call the generalized momentum, and that's the way we are going to call the generalized momentum Pj conjugated to the cyclic variable, this is conserved. So cyclic variables yield conserved momenta, and every time you see a cyclic variable that is, again, one more time, a variable that does not enter explicitly in your Lagrangian, you already know that you have a first integral somewhere, because the conjugate momentum, generalized momentum of that coordinate is going to be conserved. This in mathematics is called Noether's theorem. But we don't need to know that. I mean, she was a mathematician, and she was the first to point out this connection in a slightly different context. Okay. So let me let's just go through some examples of these things, and then I stop. For instance, if you have the question here is which component or components are conserved. And I give you, for instance, say you have a system that is described by an infinitely homogeneous plane in space, like the top of this table, but just make it infinitely big, very big office. Okay, so just by looking at the system, you should be able to tell me what are the quantities that are conserved. So your system is defined by an infinitely homogeneous plane. Yeah, but which components of the momentum? Yeah, px and y, right? Not pz, because in the z direction the system is not homogeneous, because at a certain point you have this table. Moreover, also about the angular momentum, what component of the angular momentum is going to be conserved? mz, right? Lz or whatever. How about an infinitely homogeneous cylinder? Well, let's call z, so it's like a cylinder like this, and I call z this direction. So what is you should ask yourself, what is the symmetry of the system? So first of all, it has a rotational symmetry in this direction. So the z component of the angular momentum, because you know that the angular momentum has a vector product, this is going to be conserved, because as you rotate about the axis, nothing changes, okay? So isotropy in this plane here, so that means this is conserved. Also, I mean, if you move in this direction or in that direction, actually the system is not homogeneous because you have the cylinder. But if you move along the cylinder, it is homogeneous. So the other thing that is conserved is pz. Okay? So just think, you can think of many systems, and by the symmetry of the system, you can deduce the conserved quantity. So that's, you will see, we are going to use that many, many times, because it's a very powerful concept. Because we are very good, our brains are very good at spotting symmetries and very poor at spotting conserved quantities. So you have linked something which you are by nature very good at with something that maybe you are not, but that is more useful. So we are going to exploit this property. Okay. Any question? Please. From Newton's equation. No, there you see it's more complicated. There you have to check for the system whether it is conserved or not. No, the same, I mean, everything is already there. But the problem with Newton's law that, okay, there you have the force. But it's not clear, given that force, whether you have conservation. You have to check. You have to compute the energy and see whether it is constant. So it's not simple. This is much more powerful, because in this language you have connected the energy with this invariance by time translation, and then it's very simple. In fact, you'll see in the next few weeks, I will always ask you, when you write the Lagrangian, is there any cyclic variable, I will ask. Is there an explicit time dependence or not? Because if the answer is no, there is no explicit time dependence, we will write immediately the energy of the system, and we will start from there rather than from Lagrange equations. And as I said, the energy, the momentum are first integrals, because only depends on first derivative on time, and they are easier to integrate.